This is the last lecture for the Fourier series. Okay. So let's start our last topic of the Fourier series, that is half range series. In half range Fourier series, there are two types of series. One is cosine series and the other one is sine series. So let's recall the formula of cosine series and sine series. Half range Fourier series. Two types are there. First is cosine series and other one is sine series. Okay, I am talking the half range Fourier series between the any limits. It half range means it is between 0 to L and L is any constant. So it may be 1, 2, 3 or pi. Okay, it may be 1, 2, 3 or pi. So now I am writing the formula for the half range Fourier series for 0 to pi. If our period is 0 to pi, then for cosine series, f of x is equal to a0 by 2 summation n 1 to infinity an cos nx. Okay. For a0, 2 by pi 0 to pi f of x dx, and an, that is 2 by pi 0 to pi f of x cos nx dx. Similarly, for the sine series, f of x is summation n 1 to infinity bn sin nx, and the formula for bn, that is 2 by pi 0 to pi f of x sin nx dx. So students, this is for the period 0 to pi, or I can say for the period pi. What about roll number 137? Please join division B. You are in division A now. Roll number 137. So this is the formula for the period pi, or we can say for 0 to pi. But what if our given period is L? If our period is 0 to L, then there is minor changes in this formula, that is cos n pi x by L here, right? Here 2 by L and 0 to L. In the AN, 2 by L, 0 to L and cos n pi x by L. Similarly, for the period 0 to L, for sine series, sin n pi x by L, right? And for Bn, 2 by L, 0 to L, sin n pi x by L. So, for the better understanding, let's start some example. So, before starting the example, I want to recall one more formula which we did in earlier. I want the answer from your side. Integration of e raised to ax cos bx dx. Anyone? Please raise your hand. What is the formula for e raised to ax cos bx dx? Everyone, please raise your hand who know the formula. Fast. Only 20 students are there who know the formula. What about else? See students, this is the most important formula. Yes, good. Many students are raise their hand that they know the formula. See, e raised to ax cos bx dx. This is e raised to ax upon a square plus b square, and here a cos bx plus b sin bx, right? And for the integration e raised to ax sin bx dx, the formula is e raised to ax upon a square plus b square. If we integrate with the sign, then first we have sin bx minus sign is there, b cos bx. Good. So now with the help of this formula, we will move for one example, that is find Fourier series of, sorry, find sine series. Find Fourier sine series, right? Find Fourier sine series. This is the most important word. Sine series. This is sine series. Find Fourier sine series of f of x is equal to e raised to x in the interval 0 less than equal to x less than or equal to pi. Okay, so they want sine series and the given function is e raised to x. Okay, so as we know the solution, the formula for the sine series, Fourier formula for the sine series, and the integral is 0 to pi, that is summation n 1 to infinity bn sine nx, right? And the formula for bn is what? That is 2 by pi 0 to pi, as our integral is 0 to pi, right? And f of x sine nx dx. So 2 by pi 0 to pi, our given function f of x is what? E raised to x. So e raised to x sine nx dx. And as you know the formula of e raised to ax sine bx, so by applying this formula, this example, our a is 1, multiple of x, that is a. So the power of e, that is a is 1 and b is n. So 2 by pi e raised to x upon 1 square plus n square. Here a is 1, so 1 sin nx minus n cos nx. Okay, and the limits are 0 to pi. So 2 by pi. After substituting upper limit, we have e raised to pi upon 1 plus n square. Sin n pi is 0 minus n cos n pi. If I substitute here pi, that is cos n pi. Cos n pi is minus 1 raised to n. So this is the value of upper limit. For lower limit, e raised to 0, that is 1, 1 upon 1 plus n square. Sin 0 is again 0 minus n. Cos 0 is 1. So minus n. Cos 0 is 1. So this is the value for the lower limit. So here 2 by pi minus n minus 1 raised to n e raised to pi upon 1 plus n square is equal to bn equal to 2 by pi minus n minus 1 raised to n upon 1 plus n square, and e raised to pi, right? This is first term. This one is first term, minus n minus 1 raised to n e raised to pi upon 1 plus n square. Here minus minus plus, right? So n upon 1 plus n square plus n upon 1 plus n square. So if I get n upon 1 plus n square common, then my bn is 2n upon pi 1 plus n square, and the remaining term, that is 1 minus minus 1 raised to n into e raised to pi into e raised to pi. So, Nishka, please hide your video. Nishka Sastri, please hide your video. Roll number 67. Okay, students. So this is the value of Vn. So for Fourier series f of x, summation n 1 to infinity Vn sin nx. So summation n 1 to infinity value of Vn, that is 2n 1 minus 1 raised to n e raised to pi upon pi 1 plus n square into sin nx. Students, this topic is the most easiest topic in the Fourier series, and uh, every year out of the whole chapter, one example from sine series or cosine series is there in the GTU exam. Okay, so it is the most important topic for you, and it is easy. So please be careful in this topic. If you have any query, you can ask me in chat book, in chat box also. Okay, or you can ask through WhatsApp also after the lecture. So find Fourier sine series. This is our function. Our given period is 0 to pi, right? Now, suppose our students, have you any doubt in this question? Have you any doubt? If you have no doubt, then we'll move ahead. If you have any doubt, then please ask in the chat box. Okay, okay. So, okay, no doubt. So, students, if the given function is same, but if I change the period, then suppose find Fourier cosine series. Okay, now we'll solve the example for find Fourier cosine series of f of x is equal to e raised to x in the interval 0 to L. In the interval 0 to L. So find Fourier cosine series of f of x is equal to e raised to x in the interval 0 to L, right? So as we want to find cosine series, we have to find a0 and an, right? And our integral, here there is no pi. L is any constant. So we have to apply the general Fourier series formula, that is f of x is equal to a0 by 2 plus summation n 1 to infinity an cos n pi x by L. Please students, don't forget this when your integral is in the form of 0 to L, right? So a0, as we want to find cosine series, we have to find a0 and an. So a0, formula of a0 is what? 2 by L, given integral is 0 to L, f of x dx, right? Now L is L itself. So we have to keep L itself, 0 to L. F of x is e raised to x dx. Now the integration of e raised to x is e raised to x. So e raised to x here 0 to L. Now a0 is equal to 2 by L e raised to L minus e raised to 0. So a0 is 2 by L e raised to L minus 1. Students, any doubt in the value of a0? Any doubt in the value of a0? Okay, answers are coming that they have no doubt. Okay, good. So we'll move for the value of an. That is an equal to 2 by L 0 to L 0 to L f of x cos n pi x by L into dx, right? Now 2 by L keep it same, 0 to L, our given function is e raised to x and cos n pi x by L dx. Okay, students, in this case, our a is, okay, now I want answer from your side. What is our A and B? What is our A and B? If I compare this integral with e raised to ax cos bx dx, then give me the answer. What is the value of A? Yes, answers are coming that A is 1, but what about B? A is 1, but what about B? Yes, very good. Very good, very good. Most of the students are giving the right answer. That is B is n pi by L. Very good, students. Thank you. Our B is n pi by L. Very good. So the formula of e raised to x cos bx of the integration, that is e raised to x upon 1 square plus our b is n pi by L. So n pi by L square. Here 1 cos n pi x by L plus our b is n pi by L into sin n pi x by L, right? And the limits are 0 to L. Limits are 0 to L. So now the turn for the substitution of upper limit and lower limit. So if I substitute my upper limit here, that is e raised to L, okay? In the denominator 1 plus n square pi square upon L square. N square pi square upon L square. Now here cos, if I put here L, then both L will be cancelled and cos n pi. Cos n pi, that is minus 1 raised to n. If I put here L, both L will be cancelled and sin n pi is 0. So 0 into n pi by L, n pi by L into 0. So this is the value for the upper limit. Minus for lower limit, if I put here e raised to 0, that is 1, 1 upon, this is 1, this is 1, so 1 upon 1 plus 1 upon 1 plus n square pi square upon L square. Here cos 0 is 1 plus sin 0 is 0. So again n pi by L into 0. So this is the value for lower limit. If I take LCM here, that is e raised to L into L upon L square plus n square pi square. 2 by L, keep it same. Here e raised to L square in the denominator. L square plus n square pi square. This one is 0, so minus 1 raised to n, right? Into minus 1 raised to n. Similarly, minus, if I take LCM here, this is L square upon L square plus n square pi square and into 1. This n pi upon L into 0 is 0, so into 1, so no need to write 1 here. Okay. Now, if I take L square common, okay, if I take L square common, then 1 L will be cancelled. So just 2L is there. Okay. And in the denominator, LCM is L square plus N square pi square. So 2L, this L, and we get the L square common, so 1L will be cancelled. So 2L upon L square plus N square pi square, and the remaining term is e raised to L minus 1 raised to N minus 1. So this is the value of an. Okay. Now we have to just substitute the value of a0 and an in our cosine Fourier series. So cosine Fourier series is f of x is equal to a0 by 2 summation n 1 to infinity an cos n pi x by L. Students, please don't forget to write this theta because our given integral is 0 to L. Okay, now what is the value of A0? So value of A0 is here 2 by L e raised to L minus 1. So here 2 by L e raised to L minus 1 upon into 2, right? Now summation n 1 to infinity. And what about the an? Our an is 2L upon L square plus N square pi square. Here e raised to L minus 1 raised to N minus 1. So 2L upon L square plus N square pi square e raised to L minus 1 raised to N minus 1. Okay. Into cos N pi x by L. After simplification, both 2 will be cancelled. So e raised to L minus 1 upon L. Here 2 upon 2L upon L square N square pi square is constant. So 2L upon L square plus N square pi square in the summation n 1 to infinity. Oh, we can't do here n is there. So we cannot write in the common. We just put 2L here. Summation n 1 to infinity e raised to L minus 1 raised to N minus 1 upon L square plus N square pi square cos N pi x by L. So this is the expansion of cosine Fourier series for the given function e raised to x in the period 0 to L. Okay. So students, have you any doubt? Have you any doubt? Please confirm in the chat box, everyone. I want the confirmation by all of you. Okay. So, okay. Most of the students are confirming that they have no doubt. So, we'll move with one more example, that is for the half range series, but it is for the discontinuous function. Okay. Now we'll do one more example for sine half range series, but for the discontinuous function. So that is, find the half range sine series of f of x is equal to x, where x lies between 0 less than x less than 1 and 2 minus x, where 1 less than x less than 2. Okay. Hence deduce that pi square by 8 is equal to 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square plus up to so on. Okay. So students, first when we start the solution of any example, first we have to check what we want to find. We want to find a half range sine series. Okay. We want to find half range sine series. It means we want to find just Bn only. Okay. And then next you have to check your given integral. Your overall integral is what here? 0 to 2. Your integral is 0 to 2. It means this is half range. So your integral, so this, it means your integral is 0 to L form, right? So you have to apply formula for 0 to L. So let's start the solution. As we want to find a sine series, it means f of x is equal to summation n 1 to infinity bn sine n pi x by L. As our overall integral is 0 to 2, so this is from, we can say this is from 0 to L, right? So the formula for bn, here 2 by L, 0 to L, f of x sine n pi x by L dx. Students, as I say, our overall integral is 0 to 2. Our overall integral is 0 to 2. It means your L is 2. It means your L is 2, right? So, as L is 2, we have to put 2 by 2. So, 2 by 2 is 1. 0 to 2. What is your f of x? Uh, Devanshi, one doubt. Devanshi, we are doing the example of half range, right? So in half range, I said earlier, in half range, see this slide. When I start our today's session, I told you in half range, only two types of range is there. In half range series 0 to L, okay, or in L we replace by 1, 2, 3 or 5. So in half range there is no 12, there is no 12. Okay, now got it? Okay, so okay, here our L is equal to 2, right? Now f of x is, what is our f of x? Here our f of x is a discontinuous function. So for 0 to 1, for 0 to 1, our integral is x, right? Sine n pi x by L, L is 2. So we keep 2 here. And for 1 to 2, as our given function is discontinuous, we have to split our integral in two terms. 1 to 2, our given function is 2 minus x into sine n pi x by 2, as L is 2, into dx. So, students, have you any doubt till this step? Have you any doubt till this step? Please, students, if anybody have any doubt, confirm in the chat box. If no doubt, then we'll move ahead. Okay. So, as our given integral is discontinuous, given function is discontinuous, so we split our integral into two steps. Okay. So, let's start for the first step. So, as 2 by 2 is 1. So, and our first integral is x into sine n pi x by 2. So, in first step, we apply Leibniz rule, x keep it same, and the integration of sine, that is cos n pi x by 2, right? So, x keep it same, minus cos n pi x by 2, and instead of write n pi by 2 in the denominator, I put 2 upon n pi in the numerator, right? minus the derivative of x is 1 and the integration of this minus cos n pi is minus sine n pi x by 2 into 2 upon n pi whole square, and the limits for the first step, that is 0 to 1. Similarly for the second step, here again we apply Leibniz rule. So 2 minus x keep it same, and the integration of this sign is minus cos, right? So 2 minus x keep it same. Integration of sine is minus cos n pi x by 2, and instead of writing n pi by 2 in the denominator, I put 2 upon n pi in the numerator, minus the derivative of 2 minus x is minus 1. The integration of minus cos, that is minus sine, theta will remain same. So n pi x by 2 into 2 upon n pi whole square. And the limits are now 1 to 2. Okay, students, have you any doubt in this step? If you have any doubt in this step, please confirm in the chat box. Okay. No doubt is there, right? So we'll move again. Now, for the first step, if I substitute my upper limit is there, here 1, and in the place of this 1, I have cos and pi. And as you know, the I have cos, if I put here 1, that is cos n pi by 2, right? So, cos n pi by 2. And what is the value of cos n pi by 2? Anyone? Uh, Most of the students are saying that the cos n pi by 2 is 0. But that is wrong, because if I take n is equal to 1, then pi by 2, so it is 0. But if I take n is equal to 2, then, so students, cos n pi by 2, we can't say, because it depends on the value of n. It depends on the value of n. If n is 1, then 0. For n equal to 1, it is 0. For n equal to 2, then that is cos pi. So it is minus 1. For n equal to 3, it is 1. Okay. So it's not a any defined value. It's very according to the value of n. So we keep cos n pi by 2 as it is. Okay. So by substituting the value of upper limit in the place of x, here 1, this one is minus. I keep cos n pi by 2 as it is, 2 upon n pi. Okay. Now, if I put here 1, right? If I put here 1, then again the sine n pi by 2, and it depends on the value of n. So minus minus plus sine n pi by 2 into 2 upon n pi, right? Minus for the lower limit, that is 0. So here 0 into anything is 0. So this is the value of upper limit, and for the lower limit, my first term is 0, minus minus plus, sine 0 is again 0, right? So this is for the first step. Now for the second term, if I put 2, that is upper limit, right? So 2 minus 2 is 0. So 0 into anything is 0. So in the second term, in the second step, my first term is 0. 3 times minus here. So minus, if I put here 2, then both 2 will be cancelled and I have sine and pi. And as you know, sine and pi is always 0. Okay. Ma'am, Parmit has one doubt. Ma'am, it's 2 upon n pi raised to 2 near sine. Uh, just a minute. See, okay, this one sine, okay, square, right? This is square. Here 2 upon n pi. If I put 1, so sine n pi by 2, this is minus minus plus, and here 2 upon n pi whole square, right? And for the lower limit, both term will be 0. Now in the second step, if I substitute my upper limit, then my first term will be 0. If I substitute 2 in the second step, then sine n pi and sine n pi is again 0. Now for the lower limit, so if I substitute 1 here, so 2 minus 1, that is 1, and for 1, that is minus cos n pi by 2, right? Into 2 upon n pi. And in the second step, if I put 1, then sine n pi by 2, 3 times minus here, so minus sine n pi by 2 into 2 upon n pi whole square. Okay, so this is for the lower limit. Now, after simplification, here minus cos n pi by 2 upon 2 n pi minus cos n pi by 2 upon 2 upon n pi. This is plus sine n pi by 2 into 2 upon n pi whole square. Here minus minus plus, right? Minus minus plus. So plus cos n pi by 2 into 2 upon n pi, and the last step, that is again 1 minus minus plus, so plus sine n pi by 2 into 2 upon n pi whole square, right? So both first and third term will be cancelled out, and second and fourth are same. So 2 times is equal to 2 times sine n pi by 2 into 2 upon n pi whole square, right? 2 times. So here 2 square, that is 4. So 4 2s are 8. So final Bn equal to 8 upon n square pi square sine n pi by 2. So this is the value of Bn. So our formula, Fourier series formula, that is summation n 1 to infinity. Bn is 8. Bn sine n pi x by L, and as summation n 1 to infinity, Bn is 8 upon n square pi square sine n pi by 2 into sine n pi x by 2. Okay, as this L is 2 here. So this is the Fourier series for the given uh, discontinuous functions, right? But we want to deduce this equation only. For that, we represent this equation in the series form by the substituting n equal to 1, 2, 3. So for that, first we take 8 upon pi square common. Okay, 8 upon pi square common. And then if I put 1, 2, 3 respectively, then my first step is sine pi by 2 into sine n and into sine pi x by 2 upon 1 square. And then for 2, then for 3, right? So here Bn is equal to 8 upon pi square. If I put 1 first, then sine pi by 2, then sine pi x by 2 whole by 1 square. For 2, I have, if I put 2 there, then see, for n is equal to 2. If I put here 2, then both 2 will be cancelled, right? And then I have sine pi, and sine pi is 0. 0 into anything is 0. So uh, the next step for the 3. For 2, I will get 0 answer. So for 3, I have sine 3 pi by 2 sine 3 pi x by 2 upon 3 square. Similarly, for the 4, I will get 0 answer. So I put 5 sine 5 pi by 2 sine 5 pi x by 2 upon 5 square up to so on. It means, students, we get the series for odd n only. Okay, for even n, the term will be 0. Any doubt? For even n, for even n, our term will be 0. If I put here 2, then both 2 cancel. So sine pi is 0. If I put here 4, then sine 2 pi, and sine 2 pi is 0. If I put here 6, then sine 3 pi, that is also 0. So for all even n, 2, 4, 6, 8, this is 0, and 0 into anything is 0. So for even n, our all term is 0. So we get only for odd n. Which step? Vidhi, I am going to unmute you. Please ask your doubt. Yes, Vidhi. What happened?
No, ma'am, I don't have any doubt.
Okay. So, uh, this is the series, but now sine pi by 2 is, student, sine pi by 2 is 1. Sine 3 pi by 2 is minus 1. 5 pi by 2 is 1. So, 8 pi 8 upon pi square, this pi by 2 is 1, so we have sine pi x by 2 upon 1 square. This 3 pi by 2 is minus 1, so sine 3 pi x by 2 upon 3 square. 5 pi by 2 is again 1, so sine 5 pi x by 2 upon 5 square, then minus, okay, and move on. Now, as we want to prove that series, and our function is discontinuous at 1, right? Our function is discontinuous at 1. So at x is equal to 1, at x is equal to 1, see, what is our given question? Our given question is, our function is discontinuous at 1. So at 1, for 0 to 1, given function is x. And for 1 to 2, our function is 2 minus x. So what about at exactly 1? So for that, we have to take the limit. That is, we have to find the value of f of 1, right? And for the value of f of 1, we have the formula 1 half limit x tends to 1 minus f of x plus limit x tends to 1 plus f of x. That is, if we take x tends to 1 minus f of x, so for the given function, our 0 less than x less than 1, it means 1 minus. For 1 minus, our function is x. And if we put in the place of x 1, so our left hand side value is 1. For 1 plus, for 1 plus, what is our function? For 1 plus, it means our given function for 1 plus, that is between 1 to 2. Our given function between 1 to 2 for 1 plus is 2 minus x. So if I replace this x by 1, that is 2 minus 1. So 2 minus 1 is there. So here for limit x tends to 1 plus 2 minus 1 upon 2, and after simplification my answer is 1. So f of 1 is 1. So here f of x is equal to, by putting x is equal to 1 in x is equal to 1 in this star, okay. Okay, but before this is the value of bn, this is the value of f of x, right? So this is, just a minute, this is the f of x. So this one is f of x. So if I put f of x at x is, and what is our f of x? Our f of x is, if I put x is equal to 1, so here f of 1. So and f of 1 is 1. So by taking 1 both the side, here I have f of 1, right? And f of 1 is 8 upon pi square. Here sine pi by 2 upon 1 square minus sine 3 pi by 2 upon 3 square plus sine 5 pi by 2 upon 5 square minus up to so on. And as you know, the value of f of 1, which we find, that is 1. Value of f of 1 is 1, right? So, here 8 upon pi square, here sine pi by 2 is, if I take by what, pi by 2 is 1, 1 upon 1 square. Sine 3 pi by 2 is minus 1, so minus minus plus, so 1 upon 3 square. This is again 1, so 1 upon 5 square plus up to so on. So our final answer for the deduction, that is pi square by 8, 1 upon 1 square, 1 upon 3 square plus 1 upon 5 square plus up to so on. So this is the formula which we want to deduct. One query is there. Why 1/2 is taken in f of 1? See, Unnati, if our limits x is equal to 0, less than or equal to x, less than or equal to 1, and 2 minus x, 1 less than x, less than 2, then we have a specific value at 1. But in our given question, there is no specific value at 1. This function is lies between 0 to 1, and this function is lies between 1 to 2. So specific value at 1, there is no defined specific value at 1, right? Therefore, we take the average between these two functions, that is 1/2 limit x tends to 1 minus f of x plus limit x tends to 1 plus f of x. So we are taking average of these two. Okay, now got it? Unnati, now got it? Okay, so students, today we conclude our lecture, and this is now onwards we move for the another chapter. Now Fourier series is complete today. For any query regarding Fourier series, we will arrange once a day specially for your doubt session, right? So you can ask in that lecture.